Assalamu alaikum. In the previous video, we have learned about vectors. We know vector is a quantity which possesses both the magnitude and direction. In this video, we will discuss about components of a vector. To discuss about the components of a vector, we must know how to represent a vector geometrically. To represent a vector geometrically, we take a coordinate system. Coordinate system is nothing but a system or a set of axes. Here, x-axis, y-axis, and a z-axis together form Cartesian coordinate system. Okay. And it is used to find the position of any moving object. Okay. Now, here I draw a line with the arrow head. This line actually represents a vector. This is the geometrical representation of a vector. The starting point of this line is referred as tail, and this point where it ends is called as head of the vector. Now let me give some name to this vector. I call it as vector E. Okay. Now I told you a vector quantity possesses both magnitude and direction. What is this magnitude? Magnitude is nothing but the length of a vector. The length of this vector is nothing but its magnitude. Sometimes it is also represents the size of a vector. Okay, and here the next property that a vector possesses nothing but the direction. Here the direction of this vector is represented by the angle which it subtends with these axes. Okay, here theta is the angle made by vector A with the y-axis. It gives us its direction. Clear? Now, how one can resolve? When we represent a vector using a coordinate system, then it can be resolved into its components. Here the meaning of resolve is to split. Okay, now I am going to split this vector into its components. Right? There is one more way of representing. Suppose if I have got only two-dimensional coordinate. Two-dimensional coordinate means a coordinate system which has got only two axes, x, y, or y, z, and 2. Okay. Now we draw a line here. This again represent a vector. Okay. This is a two-dimensional coordinate system. This is a three-dimensional coordinate system. Fine. In a two-dimensional coordinate system, the vector is resolved into two components. One acts along x-axis, another acts along z-axis, y-axis. I'm sorry. So, to get the component of a vector acting along x-axis, I drop a perpendicular from the head of vector A. Okay. Just not drawn properly. This is the perpendicular which intersects at some point on the x-axis. Okay, so this one, yeah, from this point to this point on the x-axis. what do we have is nothing but AX. This is the component of a vector along x-axis. The similar way, when a line is dropped from the head of the A vector, it intersects on the y-axis. And this length on the y-axis gives us AY value, which is nothing but the component of A vector along y-axis. Understand? So, and next, the direction of A vector is given by theta, which is the angle between x-axis and A vector. Okay. So, what will be the value of AX? Now, before that, let me show you how do we represent A vector in a two-dimensional coordinate system. Here, A vector in two-dimensional coordinate system is represented as AX, just the component of A vector along x-axis plus it is added with the component of A vector along y-axis. Understand? Now, I have told you earlier, a vector quantity have got direction along with magnitude. Here, AX and AY represents only the magnitude. They must possess the direction in order to represent a vector quantity. So here, what I do, I multiply these two terms with the unit vectors, orthogonal unit vectors. The unit vector which acts along x-axis is nothing but I cap. Okay, and the unit vector which acts along y-axis is nothing but j cap. Okay, so AX is multiplied with the I cap to give direction to it, and AY is multiplied with the j cap to provide a direction to AY. Okay, so won't we get an expression on multiplying I cap? See, let me tell this to you in a clear way. Won't this change the value of AX and AY if we multiply these two terms with I cap and j cap? The answer for the question is no, it will not make any change. The reason is this unit vector have magnitude equivalent to 1. Okay, along with this, it possesses some direction. So, when you multiply this AX, this component with I cap, it only provides direction. The magnitude do not vary because it is equivalent to 1. As you know, whenever something is multiplied with 1, the value remains as such. Clear? So this is how one can represent a vector quantity in terms of its components. This is how one can resolve a vector quantity into its components. Clear? Let's go ahead. Now I will provide the magnitude of A vector. Now, the magnitude of A vector. The magnitude of A vector is represented as A, and it is nothing but root of AX square plus AY square. This equation gives us magnitude of A vector. Okay, and what is this AX and AY represent? Let's find out the value of AX and AY from this diagram. Okay, I take this part of the diagram, which is nothing but a right angled triangle. Right? This makes an angle of 90 degree. So it is a right angled triangle. Okay, for this, now to this one, apply From this I am going to find out the value of sin theta. What I will get if I do so? Sin theta is nothing but opposite side divided by hypotenuse. Here the opposite side is this. It's the value is the AY. See, just parallel to this part. If the value of this part is AY, then this one will also possess the same value. AY. Opposite side is AY. Now hypotenuse is A. Okay, so on cross multiplication, AY value will be equal to A sin theta. So this is I write here. So AY equals to A sin theta. Box this. Now, what will be the value of AX? Now, for that also, I am going to use the same equation, the same diagram. I'm sorry. Now, I take for the value of cos theta. Cos theta is the adjacent side divided by hypotenuse. Here, this right angle triangle, adjacent side is represented by this is the adjacent side. And its value is AX. That's divided by hypotenuse. Hypotenuse value is A. Okay, so AX equals to A cos theta. Okay, now I'll box this and I'll do the same thing to this equation as well. Okay, so the value of AX is nothing but this. Understand? I'll box this one as well. Now I got the value of AX and AY. Now let me substitute these two things here in this equation. See what I get if I do so. Root of AX square plus AY square. No? What is the value of? AX is A cos theta whole square plus A sin theta whole square. Okay. Then I expand this A square cos square theta plus A square plus sin square theta. This is what I obtained. Okay. So next, what I do? I take out the common term. A square sin square theta plus cos square theta. Just I interchanged their position. That is not going to make any difference. And here, we'll say sin square theta plus cos square theta is equal to 1. We have studied this in trigonometry. Sin square theta plus cos square theta is equal to 1. So, enough. What I have left here, this one, square root is missing. The next step, root of AX square plus AY square equals to root of A square multiplied with 1. So the value is A square. Okay. And next step, it becomes equal to A. Now you would have understood that we have got this expression, okay, which represents the magnitude of vector E. Okay, I box this. Now I take this diagram and I explain you the different components of a vector when it is placed in three-dimensional coordinate system. Components of of A vector three-dimensional coordinate system. Okay, three-dimensional coordinate system. Understand? We'll see. I take this one. Three-dimensional coordinate system. Here's the x-axis. We go in anti-clockwise direction this way. Start from x, y, then z. So anti-clockwise direction. Okay, and this coordinate system is called as right hand z up coordinate system. Okay. And in physics, usually we use this kind of a coordinate system. So remember, keep this in your mind. Now, this is the line which represents the A vector. So, you see carefully what I do. I drop a line from the head of A vector, which intersects the y-axis. Then the end of this one is connected to the origin. Fine. After that, I draw a line parallel to y-axis which intersects the z-axis, x-axis. Understand? After that, I draw a line almost parallel to this one, which intersects the z-axis. Now, the distance between origin and this intersecting point represents AZ, which is the component of A vector along z-axis. And here, this up to here, so this part of y-axis represents a AY. That is the component of A vector along the y-axis. The next, this point where this line intersects x-axis gives us AX. It is the component of A vector along the x-axis. Now, if it is so, how do we represent vector A in terms of their components along x-axis, y-axis and z-axis? Let me write this one here. This A vector is represented as AX multiplied with the I cap. So this is the orthogonal unit vector along the x-axis plus AY multiplied with the unit vector along the y-axis plus the component of A vector along the z-axis. That is AZ, and it is multiplied with unit vector acting along the z-axis. That is the K cap. This is the expression we obtain for A vector based on its components acting along different axes. Got that? That's it. This is how one can resolve any vector quantity into its components. Now, this method of resolving a vector quantity into its components is called as analytical method. And this method can be used for adding or subtracting a given vector. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put a question in the comment section. Thanks for watching.